Okay, so today we're going to be looking at at section 13.3 from Stewart's calculus. So what we do today is going to involve curves. Well, first of all, we're going to, of course, it's going to involve space curves. First thing we're going to do is going to look at the concept of arc length. Okay, so let's say you have a let's say you have a space curve that is parametrized by the equations ft, right? Let's say this is your space curve. Rt equals ft, comma gt, comma ht. I can find and let's say as t increases in a particular direction, right? So call this point A and you call this point B. I want to find the length of the curve between A and B. So the way to do this, and I've already given you the proof, is to break this up into tiny segments, right? Break this curve up into tinier segments and let the length of those segments go to 0. You break this up into these tiny segments that are called seconds. These are called seconds. S-E-C-A-N-T-S, seconds. And you add the lengths of the seconds, and then you let the length of the second go to 0. As in you have infinitely many intervals. So the answer to this question is S of t, meaning, I'm sorry, not S of t, the length, right? The length of the curve, between A and B is given by, from A to B, right? You take the square root f prime t whole square plus g prime t whole square plus h prime t square. I'm sorry, not whole square, square. Right, so this is actually the same as, so f prime t is of course dx over dt. I mean f prime t is dx over dt, g prime t is dy over dt, and h prime t is dz over dt. So this is actually equal to the modulus of r prime t, right? Why is the integrand? Okay, so then you integrate with respect to t. The integrand is actually equal to the modulus of r prime t. Why is that? R prime t is what? It's basically f prime t, g prime t, h prime t. So L is actually equal to r prime t dt. And of course, if you're dealing with space curves, I mean, if you're dealing with plane curves, then then of course, for plane curves, we have h prime t. I mean, h of t is equal to 0, right? H of t is equal to 0, and as a consequence, h prime t is also going to be 0. Right? So for example, if you have a curve that has the vector equation, this is example 1, r of t equals cosine t, sine t, and t, and you want to find the length of the curve from 1, 0, 0 to 1 0 twice phi. The first thing you do is you figure out the t values at each point. So t at this point t equals at 1 0 0 t equals 0 because cosine 0 is 1, sine 0 is 0, and t is 0. And at this point t is equal to twice phi. And r prime t for this curve is of course negative sine t cosine t and 1. Now if that is indeed the case, then the so this is A and this is B. Then the length is given by 0 to 1. Of course, the modulus of r prime t is something you can calculate, that this is equal to sine square t plus cos square root of 2 is equal to square root of 2 dt. Sorry, 0 to twice phi, I'm sorry, not 1. So this is equal to 2 root 2 pi. Now, the same curve, of course, the same curve C can be parametrized in two different ways. And if you, when you parameterize, so for example, R1t is equal to t square t cubed, right? So in terms of u, another variable u, this can be let's say that t is equal to e to the u. This can be parameterized as e to the u, e to the twice u. Okay, this is of course between 1 and 2, right? And this is of course between 0 u ln 2, right? E to the twice u and e to the thrice u, right? So so we make the substitution, t is equal to e to the u. So this, the range for this is of course between 0 and ln 2. So because, so when t is equal to 0, t is equal to 1, sorry, u is equal to 0, t is equal to 1, u is equal to ln 2, t is equal to 2. Okay, so you have this 0 to ln 2 range for, and when we're parameterizing in terms of u. Right, so so if we were to use this parameterization instead of this, we'd get the same answer. Right? It doesn't really matter what parameterization you use. In fact, what we can do is we can reparameterize in terms of the arc length. So since these two are the same curve actually, parameterize differently. So same curve, parameterized differently. This is what is known as a reparametrization. Okay. In fact, what we can do is we can reparameterize in terms of the arc length. Let's define the arc length function. Let's define the arc length function. The arc length function, right, as the distance from t is equal to 0 along the curve, right, along the curve. Right, so this is important, this way, along the curve. So this tells me that the arc length function, so this, what does this tell me? This tells me that the arc length function in terms of t, s of t, is given by 0 to t r prime u du. Of course, which is the same as dx over du square 0 to t plus dy over du square plus dz over du square du. Now, by the fundamental theorem of calculus, if I were to differentiate differentiate both sides of this equation, right? So by FDC, right? If I were to differentiate both sides of this equation, what would I get? I would get ds over dt equals r prime of t, right? Differentiate both sides of this equation. I get ds over dt, and using this equation, using this, I can reparameterize. Using this equation, I can reparameterize. Using this equation, what can I do? I can reparameterize by finding t in terms of s. How do we do that? So, for example, we go back to our this curve, cosine t, sine t, and t. Right? According to this curve, if you take the length of this curve, st, the length function, so this is 0 to t. Of course, r prime u, remember, was the square root of 2. Square root of 2 du, right? If you remember, and so this tells us in terms of t that this is equal to square root of 2t square root of 2t. Now hence t equals s over square root of 2. So rt, remember, was equal to cosine t, sine t, and I believe the third variable was t, right? Cosine t, sine t, and t. But rt can also be written as, let's call it, in terms of s, r of t of s. Now, since t is s by root 2, this can be written as cosine s by root 2 sine s by root 2, and of course s by root 2. So this is the process of reparametrization. Okay, so now what we're going to do is we're going to look at curvature. Okay, curvature, basically, when we study curvature, we want to study how rapidly a curve bends, or how rapidly it changes. Right, so that's basically curvature. So next section is curvature. So as you already know, each and every curve, right, has a tangent vector associated with it, right? And the tangent, of course, it grazes the curve. It does not. It grazes the curve at only one spot. It does not. What do you call it? It does not touch it at more than one. Sorry about that. Just a moment. Draw arrow. Okay, so for example, this is the tangent at point. This is a tangent at point P, for example, right? So tangent curve of the curve, this grazes the curve at only one spot, and it does not change the. It does not intersect at more than one point. The tangent to a curve, right? T of. So let's say the tangent. So this tangent, of course, is parallel to r prime t, right? This tangent is parallel to r prime t. We want to define the unit tangent vector, right? The unit tangent vector to at P, right? So the unit tangent vector at P, unit tangent vector at P, let's call it T of T. T of T, this is equal to the unit vector in the same direction as r. So this is equal to r of r prime t divided by the magnitude of r prime t. So this is guaranteed to give you a unit vector. Now, the tangent vector, it tells you what direction the curve is going in, right? So the more rapidly the tangent vector changes, the higher its curvature. Curvature is a way of measuring how far the tangent vector changes, right? So we defined the curvature kappa of a curve. Let's call it kappa. This quantity is known as the curvature. This is equal to the magnitude, right? This is equal to the magnitude of the derivative. Just give me a moment. Of dt over ds. So this tells you how fast the tangent vector changes as you move along the curve, right? So that's dt over ds. Of course, the curvature can be written as written in terms of by the chain rule. We may write dt over ds can be written as in terms of another parameter t. This can be written as dt over dt times d small t over ds. Therefore, kappa can also be written as, if you want to change the parameter, the magnitude of dt over d small t divided by ds over d small t, or it can be written as t prime t divided by t prime t is of course equal to and the modulus of ds by dt, right? Remember, the modulus of ds by dt is this, r prime t, right? The modulus of ds by dt is r prime t. So this we can write is prime t divided by r prime t, the modulus of r prime t. Sorry, the modulus of r prime t is equal to ds over dt. Right. So this is, so kappa can be written as the ratio of the rate of change of the tangent vector and to the rate of change of our RT, right, with respect to t, with respect to any parameter t. So for example, let's take example 3. Just a moment. Example 3 from Stewart's calculus. Okay, so you have r of t given by a cosine t, comma, a sine t. Right, so this one has this is a plane curve. Why? Because this is in 2 dimensions. This is a plane curve. Let's see if we can find how we can find the curvature. So r prime t is of course r prime t is of course negative a sine t times an a cosine t, right? So t prime t equals r prime t divided by the modulus of r prime t. So the tangent vector, of course, this is equal to negative a sine t, a cosine t, and this is of course equal to a. Right? This is basically a circle of radius a. It's circle of radius a. Circle of radius a. Right, so this is equal to negative sine t cosine t. Right, so so this is the I'm so sorry, this is not t prime t, this is t of t, the tangent, the unit tangent vector, right? The unit tangent vector. Actually, so t prime t is then t prime t equals negative cosine t and negative sine t. Right. So this is t prime t, and if I use the if you use this formula, kappa, of course, r t prime t divided by r prime t. So kappa would modulus of t prime t divided by modulus of r prime t. So the modulus of t prime t is of course 1. So then kappa, this is defined as, and this is the modulus, right? T prime t divided by the modulus of r prime t, which is equal to 1 over a. Okay. Notice that for the circle, the curvature, the curvature of the circle is equal to the inverse of the radius of the circle. Right. So if of course if the circle has it becomes a straight line. I mean, if we have a straight line, for example, all right, the curvature is always going to be 0. Why? Because dt over dt for a straight line, the tangent vector is a constant, right? Tangent vector is a constant, right? So t prime t is 0. So if it's a straight line, then the curvature is 0. Okay, so so this is one way of computing the curvature, but there's a more convenient way, right? There's an easier way of computing the curvature, and this is something that we're going to derive right now. we have a formula for kappa t for computing the curvature of t. New formula. For computing the curvature at t, and that new formula is kappa t. I'm going to derive this, don't worry. Kappa t equals r prime t cross, remember these are vectors, r double prime t divided by okay, so the modulus of this divided by r prime t cubed. Right? Now, how do we prove this? Let's prove this. So this is a formula. This is a formula we're going to use to compute the curvature. This guy over here. I'm going to use this to compute the curvature. Right? So let's see how we can do this. So remember, t equals r prime over the magnitude of r prime. Right? So this is the unit magnitude, unit tangent vector, and the modulus of r prime equals ds over dt times t. So the modulus of r prime is just ds over dt. This is something we found out when we defined s in terms of t. Right? So so that gives me that tells me that, and okay, so there's another formula I need to know, which is so r prime, which tells me that r prime equals magnitude of r prime, right, times t, which is equal to ds over dt times t. Now that I know this, let's find r double prime. All right, r double prime by the chain rule, right? I mean, this is a little sloppy because all of these guys are functions of t. R prime is a function of t, r double prime is a function of t, and so on and so forth. And when I take derivatives, I mean derivatives with respect to t. So if I use the Leibniz chain rule, I get so this is equal to d over dt of r prime. So this is equal to differentiate this, d squared s over dt squared times t, of course t, plus d prime ds over dt. T prime times ds over dt. So this is my r prime, r double prime. So let's find r prime cross r double prime, which is the numerator of this formula. Let's find the numerator, the thing inside the modulus brackets. This is size brackets, right? The thing inside the vertical brackets. R prime cross r double prime equals ds over dt t cross d square s over dt square t plus d prime ds over dt. Now, because t is in the same direction as t itself, I mean, if two vectors are in the same direction, remember their cross product is obviously equal to 0. So this tells me that, t cross t equals 0. So only the second term here survives. So you have ds over dt squared t cross t prime. Okay, so this is what survives. ds over dt squared times t cross t prime. Now, page after. Now we have to find the magnitude of this guy. Right, so remember so the magnitude of r prime cross r double prime equals ds over dt squared times magnitude of t cross t, right, t prime. Right, now remember that if remember that we proved before that if a vector has constant magnitude, right? If if some vector has constant magnitude, then what? Then the vector dot its derivative equals 0, right? So which tells me if a vector has constant magnitude, this means that it is at 90 degrees with its derivative, right? So which tells me, so since t has magnitude 1, remember t is the unit vector, unit tangent vector, right? So this tells me that this is equal to ds over dt squared times modulus of t modulus of t prime sine 90 degrees, right? This is a unit vector, this is a unit vector. I'm sorry, there's no guarantee that t prime is a unit vector. T is a unit vector, I know, but there's no guarantee that t prime is a unit vector. So this tells me that ds over dt squared times the magnitude of t prime. So this is what you have upstairs, right? And of course t prime can be written as t prime can be written as, sorry, prime should be inside on t, not outside of the modulus sign. The prime should be on t, right? So t prime can be written as, so this is the magnitude of t prime, not just t prime, the magnitude of t prime. This can be written as r prime cross r double prime divided by the magnitude, ds over dt squared. ds over dt squared. Alright, so this is t prime, and remember that ds over dt is the same, ds over dt, this is something we learned before, that this is the same as r prime t, magnitude of r prime t. Right, so so this can of course be written as, okay, sorry, this should be a magnitude. This can be written as this r prime cross r double prime divided by r prime squared. Okay, so so kappa, remember how we defined kappa? Kappa was defined as magnitude of t prime t divided by magnitude of r prime t. That was how we defined kappa. So in this case, so kappa is going to be magnitude of t prime t divided by the magnitude of r prime t. I'm just bringing back the t's here. So this gives me, so this is r prime t cross r double prime t So there's an r prime square here, and there's an r prime here. So this gives me r prime t cubed. Right. So this is the value. So this is a formula you can use for the calculation of kappa. So for example 4 asks you find the curvature of the twisted cubic RT is equal to t squared t cubed as a general at a general point and at 1 0 0. Right. So at a general so to find the curvature, so we're given a curve, right? RT equals t squared and t cubed. Right. So we need to find RT. RT is equal to 1 twice t and 3t square. So this is r prime t, and r double prime t equals 0, 2, and 60. If you multiply with 2, if you find the cross product between these two, r prime t cross r double prime t, r prime t cross r double prime t, this is actually equal to 60 square negative 60 and 2. Right. So this is what, and of course finding the magnitude, the magnitude of r. This the magnitude is the numerator in the in kappa cross r double prime t. This is equal to, of course, the square root of 36 t to the 4 plus 36 t squared plus 4, right? And on the denominator you have r prime t cubed, right? The magnitude of r prime t cubed, which is this. Downstairs you have r prime t cubed, which is equal to 1 plus 4t squared plus 9t to the 4 to the power of 3 over 2. So the answer is basically 2 times 9t to the 4 plus 9t squared plus 1 divided by 1 plus 4t squared plus 9t to the 4 to the power 3 by 2. So this is the curvature at the point T. Curvature at the point T, kappa T. And of course, if you want to find the curvature at t is equal to 0, just plug in t is equal to 0. Now, if you have a plane curve, right, y equals fx, right, the curve y equals fx can be parameterized as the curve y equals fx can be parameterized as plane curve can be parameterized as r of, with the variable x, rx, x fx 0, right? So r prime of x is of course equal to 1 f prime of x 0, and r double prime of x equals 0 f double prime x 0, right? So r so you have r prime x cross r double prime x. This equals this gives you 0 0 f double prime x, right? 0 0 f double prime x. This you can check out for yourself. Right, so the magnitude is of course going to give you, so the magnitude of this guy equals the magnitude of this guy. This is equal to f double prime the modulus of f double prime x. And of course downstairs you have r prime, this cube of the magnitude of r prime x. So downstairs you have r prime x cubed. This is actually equal to 1 plus f prime x 3 over 2. So kappa for a plane curve, kappa x equals the magnitude of f double prime x divided by 1 plus f prime x to the 3 over 2. Okay, so so far what we've looked at is we've looked at curvature, we've looked at the length of vectors. Now this next section is going to be on the length of normal, and the next section is going to be on normal and binormal vectors. Right? What we're going to do is going to have a system of 3 orthogonal vectors that are going to accompany the curve at every point on the curve. They're going to be on the curve at every point. The 3 vectors are, of course, we've seen one of them, tangent vector. These are orthonormal vectors, meaning they're orthogonal and they're perpendicular to each other. So we've seen the tangent vector. I'm sorry, they're orthogonal and they're of unit magnitude. So of course we've seen the tangent vector. We're going to have to take a look at 2 other vectors, the normal and the binormal vectors. Right? So the normal vector is defined as the derivative of the tangent vector. The normal vector is defined as okay, so now what we're going to do is we're going to look at the normal vector. Right, so remember, recall that the dot product of a vector of constant magnitude and its derivative is 0. As in if a vector has constant magnitude, then it is orthogonal to its derivative. So since t of t has magnitude 1, this tells me that t of t dot t prime of t equals 0, as in they are orthogonal, right? The normal vector n is of course perpendicular to t of t, and it is defined as, let's call this a normal vector. Normal vector, and it's defined as nt equals t prime at t divided by the magnitude of t prime at t. Remember, just because t is a unit vector does not necessarily mean that t prime is going to be a unit vector. So this is also known as a unit normal at t. We're going to define a third vector which is orthogonal to both the normal vector and the tangent vector, called the binormal vector. We'll call it the binormal vector, and this is equal to bt is equal to t at t cross n at t. Right, so this is what is known as the binormal vector. So the cross product is, of course, of t and n is of course perpendicular to both t and n. So let's have a look at the vector normal, binormal, and of course the tangent vectors. Right. So we start with for the curve, right? And we take any point on the curve. Let's call this the point P. Let's draw an arrow for the tangent vector. So the tangent vector. Let's draw an arrow for the normal vector. And the vector that's perpendicular to both is what's known as the binormal vector. Right, so you have the tangent, normal, and the binormal vector at the point T. Right, so this the directions of these three vectors are of course always changing. As you move along the curve, the directions of all three vectors is constantly changing. So as you move along the curve, the directions of the three vectors are changing, right? In fact, this is called a TNV frame, right? TNV frame. Right. So for example, if we start with R of t, this curve R of t, let's call this cosine t I, sine tj, and tk, right? So the derivative of r will of course be negative sine ti plus cosine tj, sine ti plus cosine tj plus k. So t of t this would equal to, if you calculate 1 over square. This is the example on page 909. 1 over root 2 negative sine t, then cosine t, and of course you have 1. Now t prime of t, the derivative, 1 over square root of 2 negative cosine t negative sine t 0. Sorry, I should be using angled brackets. To denote vectors, we should use angled brackets. Right. T prime t is this. Right. So n of t equals t prime at t divided by the magnitude of t prime at t, and this is going to be equal to negative cosine t negative sine t and 0. These are the three components of n of t. The binormal vector b this is of course equal to t at t cross n at t, and this if you do the cross product, you end up with 1 over root 2 sine t negative cosine t and 1. If you have to just do the cross product. Okay, so let's look at example 7. In fact, I I expect you to go through example 7 yourself. You can compute t. You have to compute t, the normal and binormal vectors, and the curvature at 1, 0, 1. Okay, so far we've looked at the t and b frame. We've looked at the three vectors: the tangent, the normal, and the binormal vectors. We looked at the t and b frame. The binormal vectors, of course, has magnitude 1, because remember, the binormal vector is defined as the tangent vector, and the binormal vector is defined as tangent vector cross the normal vector, right? And the magnitude of this is the magnitude of the tangent vector, right? Times the magnitude of this guy times sine theta. But theta is 90 degrees. Why? Because these two are orthogonal. Right? These guys are orthogonal. So, and of course, this is 1, this is 1. So this is equal to 1. Right? So the binomial vector has magnitude 1. It's guaranteed to have magnitude 1. Okay, so next we'll have a look at a few planes. We'll call them the we'll have a look at a couple of planes, the normal plane and the osculating plane. So let's define the normal plane first. Okay, so the normal plane is the plane that contains t, the tangent vector, and the normal vector. Right? That's the normal plane. And the osculating plane is the plane that contains the normal vector and the binormal vector. Right? So for example, instead of drawing this, let me just show you the figure from a textbook. So this is a T and V system: tangent, normal, binormal. Right, and of course at other. So at this point, this is the tangent, this is the normal, this is the binormal. Some other point the tangent is different, so hence the normal and the binormal are both different. So of course this is extremely important when it comes to differential geometry. When you're studying curve theory and differential geometry, curve theory, right? This is basically the introduction to curve theory in differential geometry. And so this is the osculating plane, the plane defined by the normal and the tangent plane, and the binormal and the normal plane is the plane defined by the binormal and the normal vectors. Now, okay, the name, of course, comes from osculum in Latin, which means to kiss. It's because this plane, this osculating plane, it contains most of the circle and most of the curve, right? So that's why it's called the osculating plane. Osculating plane. Osculating plane. Right. Now the circle of curvature, or the osculating circle, is a circle that is tangent to the curve, right? It passes through P, right? The circle passes through the point P, and I'm sorry, it's not necessarily tangent to the curve, but it passes through the curve at that point P and has a radius of 1 over kappa, where 1 over where kappa is the is of course the curvature. 1 over kappa. 1 over kappa is this quantity known as the radius of curvature. Radius of curvature. Okay, so we can think of so if the curvature is very large, meaning the circle is varying, the curve is changing tangents very rapidly, right? Such as over here, right? Curvature is very large, so the circle of curvature is very small. It has a very small radius. Now, if the curvature is very small and the curve is varying very slowly, then the circle of curvature is very large. For example, example 8, right? It asks you to find the equations of the normal plane and the osculating plane of the helix of example 6 at the point P 0, 1, pi over 2. Okay, the point P. So we have a helix, right, of example 6, meaning this helix r of t equals cosine ti plus sine tj plus tk. We want to find the osculating plane and the normal plane. All right, yeah. Okay, so so let's first find the osculating and the normal plane. Okay, so of course we need to find the osculating plane. We need t and n, right? For this, I need t and n, right? So t is equal to this. This is n, right? This is equal to n. No, this is actually r prime t. This is not equal to n. This is parallel to n. Parallel to n. We don't need n. We just need the direction of t and the direction of n. We just need the directions of t and n. Directions of t and n. Sorry, this is not parallel to n. This is parallel to t. I'm really sorry. This should be parallel to t. R prime is parallel to t, right? And and the normal plane. Okay, so the normal plane. So t is of course perpendicular to the normal plane, right? And right? So t is perpendicular to the normal plane, and r prime is of course parallel to t. So this is the equation of the normal plane, or z equals x plus pi over 2. Now the osculating plane is of course contains t and n. So vector to so v is perpendicular to the osculating plane, right? And v is equal to this, and v pi over 2 is this. So if this is perpendicular to the osculating plane, then this is using the dot product, right? X minus 1 over root 2, right? X minus 0, right? Plus 0, x minus 1 plus 1 over root 2. Sorry, 0 y minus 1, 1 over root 2 z minus pi over 2 equals 0, or z equals negative x plus pi over 2. So if z equals x plus pi over 2 is the normal plane, and z equals negative x plus pi over 2, the osculating plane. Of course, then there's the osculating circle. We can find the osculating circle at the origin, right? So this y equals x squared passes through the origin, and at the origin, you can figure out that kappa 0 equals to 2. Alright? So since kappa 0 equals to 2, the radius of the circle of curvature, the osculating circle, is 1 over kappa 0, which is half. Now, if you move a distance of 0, 0, sorry, if you move a distance of half in this direction, in the direction of the what? In the direction. Oh, okay. There's just this one clarification I need to make. When I say distance 1 over kappa from P, right? From the point P. I mean along the vector n, right? So if this is the vector n, you move 1 over kappa along in this direction. If this is a vector n, you move 1 over kappa in this direction. So if n is 0, 1, right? So you move along this direction in the direction of the normal vector, which is along the y-axis, and of course you end up here at 0, half, right? So 0, half, 0, half, center is 0, half, center of the oscillating circle, and the what do you call it? The radius is equal to half, right? Which gives us a circle x squared plus y minus half squared equals 1 over 4. And okay, so here we summarize all the formulae for so this is a tangent vector, this is a definition, this is the other definition, this is another definition, right? Tangent, normal, binormal, right? And this is something we derived for kappa, right? So this is kappa is equal to this, which is equal to defined to be equal to this, which is equal to this, which is equal to this. So this is something we derived, right? This is we showed, or we derived this formula. Okay, now curvature. Of course, curvature tells you how far a curvature tells you how fast the tangent vector changes, right? Meaning how much the curve bends. Now, t is of course normal to is a normal vector. I mean, since t is a normal vector for the normal plane, meaning t is normal to this green plane over here. T is normal to this green plane. So the tangent vector at P rotates in the direction of n, right? The tangent vector is always moving in the direction of n, because dt over ds is parallel to n. So as P moves along C, the tangent vector P rotates in the direction. Okay. Now a space curve, it can also twist, or it can lift out of the osculating plane, meaning so if you have a plane, so the oscillating plane, remember I said that the oscillating plane is a plane that contains most of the curve, right? So the space curve tends to lift off the oscillating plane. We call this lift twisting or torsion, right? And since V is normal to the oscillating plane, dV over ds, it tells you how that oscillating plane changes, right? It gives you information about how that oscillating plane changes, and the so dV over ds, you're going to show that this is equal to negative tau n, where tau is a number called the torsion, and tau equals negative dV over ds dot n. Right? So so if you take so what happens if you take so n is a unit vector, of course. So n dot dV over ds equals negative tau n dot n. So n is a unit vector, so this is equal to negative tau. Right, so tau equals negative n dV over ds. Okay, so the torsion actually tells you how much of a curve twists, right? So there's bending and there's twisting. So twist out of the oscillating plane or into the oscillating plane, right? So so it gives you a measure of how it gives you a measure of how the it's related to how the oscillating plane changes, Right. So to how the oscillating plane changes is how as you go along the curve. Okay. So now of course torsion, we could compute the torsion using the chain rule. Okay. So torsion is given by tau equals negative dV over ds dot n. Right? Tau equals negative dV over ds dot n. Torsion. Yes, this is the torsion formula. Now, of course, you can write using the chain rule that dV over dt equals ds. I mean, for ordinary derivatives, you can think of the chain rule as cancelling differentials, right? And which leads you to dV over ds equals dV over dt divided by ds over dt, which is b prime t over, remember ds over dt we calculated to be the magnitude of r prime t. Okay, so tau of t is negative v prime t dot nt divided by the magnitude of r prime t. Right, so that's because v prime t divided by r prime t is just my dv by ds, right? And of course there's a dot n here, dv by ds dot n, so negative dv by ds dot n. Okay, so what have we left? Right, so we have left this bit. Find the torsion of the helix rt equals cosine t sine t and t. So let me so I'll write down these definitions in your in the PDF notes, and I'll just upload them later on. Okay, so find the torsion of the helix. So the torsion of the helix is we know ds over dt, so we can use this as a working definition for the torsion, right? So we can find ds over dt. We can using that we can find nt and vt, right? And then from there we can find v prime t, and we end up with we know nt, vt, and ds over dt. So from there we can find tau, which is equal to half. Okay, now notice something here. The torsion shows the unit circle RT. Figure 13 shows the unit circle RT and the xy plane, and figure 14 shows the helix of example 10. Right. Notice that for the circle, torsion is 0. It does not lift out of the plane, right? But if the torsion is, notice the torsion here is half and it lifts off the plane. But this is for the helix, and this is for the circle. Right. So, and of course, there's a proof. There's a theorem here that gives you another formula for the torsion, just like you had a formula for you have a formula for the curvature, and of course the proof is an exercise left to you. That's for your assignment. Okay, so we've looked at curvature, torsion, and the TNV system. So that's it for this lecture. After this, I'll give you your assignments. Okay, so thank you very much.